Are you ready?
I am ready.
Okay, so just for our members, we do have a few updates to let you know about. First, the dues for HOI membership for 2021 will be collected at the start of the new year. There should be an email reminder that will be sent out soon, which will include an address or other means for paying your dues. Remember that you're considered a member of HOI when your annual dues are paid, and you can receive certificates for the operator CEUs for these presentations only if you are a paid member of HOI. There is an update for Illinois EPA as well in regards to certificates. There is a restructuring that's occurring at Illinois EPA. Debbie Alderman, who has been responsible most recently for operator certification, is retiring. So as a result, the water and wastewater certification departments will be combined at Illinois EPA going forward. And as a result of that, all wastewater exams that were scheduled for December have been canceled. So if you are an operator or you know an operator who has signed up for the December exam, they will be notified of the cancellation and that test will be rescheduled. Also, Illinois EPA is updating the operator database, and as a result of that, the agency is asking all wastewater operators to make sure that their personal information is up to date in that Illinois EPA database. If you have any questions regarding those updates, you can contact the operator certification unit at Illinois EPA. So without further ado, we have today Mr. Todd Holtz from SJE presenting to us. Thank you, Todd, for volunteering to present. Mr. Todd Holtz joined SJE in 2015 when SJE acquired ICS Healy Ruff, a manufacturer and integrator of control systems for municipal water and wastewater applications. Mr. Holtz is currently the Vice President of Sales, Engineered Systems Division. He has more than 25 years of municipal controls experience, and during his career has been responsible for project management, design engineering, programming, and sales management. Mr. Holtz holds a bachelor's degree in electrical engineering from Minnesota State University, Mankato. Okay, Todd, take it over.
All right, thanks, Brandy. Well, that was pretty formal. So, in reality, the way I like to conduct these, most of the time it's in person. So I thank everybody for hopping on a virtual. It seems to be our new normal. But if you do have questions, by all means, go ahead and unmute yourself and ask at any time. I'll pause kind of in between each slide as we go through just to see if there are any questions. The unmute button, at least on my screen, is up in the upper right part by the microphone. So the title of this presentation is Control Panel Components and the Component Function. So we're going to spend a little bit of time going through the following components and everything. We're going to start a little bit with electrical safety. We're going to jump into transfer switches, breakers and disconnects, a little bit on surge protection, phase monitors, motor control, transformers, power supplies, and then go into PLC controllers, barriers for UL 698 applications, and then the closing has questions and answer. But this is pretty informal, so if you do have questions, by all means, if there's a component that you would like to discuss that's not on here, by all means ask, and we can spend a little bit of time on that. So going forward here, the first couple slides are just going to show a little bit of what componentry is in panels and different kind of images of different types of panels. So here's some photos that I'll just bring up here. The first one basically showed a back panel. It's a pretty typical lift station type panel where you have breakers, starters, overloads, and then your CPT or control transformer in the panel with all your control circuitry located here in the left-hand part of that. The next photo kind of shows an inner door, showing those same breakers coming through for the pump breakers or main and emergency in this situation. And then you have some pump breakers and all the control circuitry here for the pilot lights, runtime meters, and et cetera on the left-hand side. Just another back panel showing some more of the components. And this is just more of an RTU / PLC type back panel. So different things. And so we'll just continue here. So the first thing I kind of want to spend a little bit of time on is electrical safety. Arc flash has become a big thing. Short circuit analysis has become a big thing. And with any panels, you know, electricity is the #1 issue, right? We need to approach it that each one can be very dangerous. If you're not comfortable going into those type of panels or those type of situations, by all means, get somebody that's qualified, electrician, somebody else in the organization. You know, everybody is of the opinion that the electrical shock, the voltage is going to get you. The higher the voltage, the more painful things are going to be. Well, in reality, that is not true. It is actually current that is your demise. So looking at this chart here, you can see that just, you know, we're talking milliamps. We're not even talking amps. But, you know, if you even get 20 milliamps of a shock that comes through you or current, you could have loss of muscle control. So I like to approach, you know, when I first started in this industry, I thought I could go into any panel and do anything without shutting the panel off and going in until you get shocked a few times. And then you kind of learn a little bit as you go. But so I'm trying to prevent other people from kind of living by my past sins, but current is the #1 issue when we're going into panels and issues. So I don't care if it's a 120 panel, if it's you know, 480, 230, current's the #1 thing. And that's why, you know, there's been a huge push lately on short circuit and arc flash analysis. And then by doing those fall into the realm of developing what they call PPE, so your personal protection equipment. You know, we've been hearing a lot about that with the doctors and nurses on the whole virus situation, but we also have PPE requirements for panels. Those are all generated based on short circuit and fault that are done by third parties more times than not. But on the right-hand side here is just some warning labels that you can see that would result from a short circuit analysis and also arc flash analysis. So it used to be there was PPE 1, 2, 3 or 0, 1, 2, 3 with 0 basically meaning you could go in with just you know, gloves, proper clothing, cotton shirt, those type of things. And they've kind of refined that a little bit. So it's based on the energy that's stored and available that could cause issues. So, you know, this sticker right here kind of shows you, you know, it's in calories per centimeter. And here it shows you need a hard hat, a face shield, safety glasses, and ear canal inserts. And then you should also have a long sleeve shirt that's arc flash rated, all those things. So most of the time in going into these type of panels, it's just good to know what's available to cause any issues. If you're talking a 230 volt, 480 volt, you know, type panels, which are pretty common on lift stations, having the proper PPE when you go into those is critical. So any questions on the electrical short circuit or anything that way? Just trying to make awareness to that before we actually jump into the panel components. Okay. So the first item is, I'm just going to bring all these up so that we can see those. So transfer switch, what is it really designed for? What types are out there? So a transfer switch is really used to connect or select between two different power sources. That's pretty prevalent in, like I said, lift station control panels. The transfer switch can come in a couple different flavors, manual or automatic. They may be service entrance rated. And again, like I stated, they connect common power sources of utility and or a generator. Some of the, let me get through here. So sorry about that. So here's kind of what a typical manual transfer switch could look like. It's got two breakers here. Your main breaker on the left, your emergency breaker on the right. The emergency top side of the emergency breaker is going to the generator receptacle. There's a slider here that slides between the two breaker on-off switches on there, so that if it's slid to the right, the breaker on the left is not operable. If it's slid to the left, then the breaker on the right is not operable. So that's one way of doing that. Just another picture of the same type of thing with it showing through the inner door. Here's one, sorry that the picture's a little blurry, but another interlock that's actually from the manufacturer that shows these are shafts so that it's going through the inner door. So when you twist the one with a pistol grip or on the inner door, there's a interlocking mechanism here that only allows one to be on versus the other. And this is what it would kind of look like through the inner door. The other type is an automatic transfer switch. Same thing as the manual transfer switch, switches between two different power sources. The biggest difference between an automatic transfer switch and a manual is the automatic transfer switch has tie-ins to also automatically start the generator. So there's always a generator normally on site. They're interfaced directly to the generator control panel. So when loss of utility power comes in, the generator will start up, or the transfer switch will detect that. It will send the signal to the generator. The generator will start. Once the generator is up to speed and can handle the load, it will then transfer the load from the utility power to the generator. And then once the utility power were to come back, it's also monitoring that. And once that comes back, it will automatically switch back to utility power and shut the generator off. Most of the transfer switches that we are using are what they call the delayed transition. A delayed transition transfer switch just means that there will be a drop in power switching between utility power, generator power, and generator power back to utility power. They do make closed transition transfer switches. They're extremely expensive, and those have a zero delay, so they're basically a bumpless transfer going back and forth. So typically in our industry, we're going with what they call an open transition. So there will be a dip in power. So when you're designing panels and going through control circuits, you need to make sure that you take that into account so that you don't automatically have a whole bunch of equipment starting at once or not starting at all. Any questions on transfer switches or automatic transfer switches in general before we move on to the next topic? Well, you're a pretty easy crowd today. Must be Friday. Next item that's pretty prevalent in most panels are what we call circuit breakers. They also have another name called overcurrent protection devices. So you'll see that circuit breakers are probably more prevalent in that realm. you're going to have a variety of flavors: 1-pole, 2-pole, 3-pole, single phase, which basically single phase, the 3-phase type, 120 to 480 here in the States, 577 in Canada. They're primarily used as a mechanism in which to shut off power and or control power. So basically, when most panels you're going to have outside, the panel, you could have a main breaker that's located outside the control panel, and then the control panel's just got lugs only that come in and then may go to two, if it's a duplex panel, 2 circuit breakers in the panel. So I'm going to throw this question out and see if anybody's got the answer, but does anybody know kind of what the difference between a thermal and a thermomagnetic breaker is?
You can put your answer in the chat box, it looks like, or you can unmute yourself.
Yep, if you just unmute yourself, then you're free to talk. But if nobody wants to take a swag at it, I can continue on, but I thought I'd throw that out there. Okay, so basically, the circuit breakers are going to be, for the most part, what we're using are going to be either thermal or they're going to be thermomagnetic. So thermal is just like you think it is. It's all based on heat. So it's going to be based on your current draw going through that breaker. So those are primarily used for overcurrent type situations in which you have a jam motor or something like that, where there's going to be an exorbitant amount of heat being generated on the conductors, and it's designed to protect the conductors and the motor downstream. So if you think of it as just in an overload type situation, there's a little bimetallic device in that breaker. As the heat generates based on the overcurrent situation, it will eventually warm up enough and expand that bimetallic contact will close and cause the breaker to open. So that has got a long time delay on it. So it's not ideal for connecting or for protecting motors, but it will work if that's all you have. And that's why there is also called the thermomagnetic. So the magnetic side of that is more for short circuit or instantaneous overcurrent or inrush coming in when you start a pump. So if you think of the magnetic part being an iron core, just like a magnet with a wire wrapped around it, as the current flows through that magnetic core, it also generates a magnetic field which then would open up the breaker as well. So thermal is more for just overcurrent. Magnetic is really for instantaneous. So that's how I kind of keep the two together, and that's why most of our breakers that we see are thermomagnetic and not just thermal. So it provides 2 forms of protection to protect the conductors and anything downstream of that. Any questions on that? Comments? Okay, moving on then. The other thing that you're going to hear with breakers is interrupting capacity. So I always like to throw out, just kind of what is the definition of interrupting capacity. So that is basically the definition is it's the maximum fault current that can be interrupted by a breaker without failure of the breaker. So you're going to hear terms when you're talking interrupting capacity of 5,000 amps or 10,000 amps or 42,000 amps, right? So that is the interrupted capacity that breaker can sustain without causing damage to the breaker or anything downstream. Why is that important, right? So it's important because a few years ago, UL and NFPA came out and said that panels also have to have an SCCR rating. And So what's an SCCR rating? Well, the rating of the panel, it's a short circuit current rating is what SCCR stands for. And the difference between an interrupting capacity and an SCCR is an SCCR is all the components or the components within the panel that make up that number, where the interrupting capacity is just for that particular component. And so my example is you have this breaker, you have a motor starter, and let's say that the normal SCCR of that panel is going to be determined by the available fault current from the utility, right? So whoever is providing power to that panel will be able to provide or tell you what the interrupt rating should be, or the fault current available for that panel should be at that particular location. So typical, like I said, 5,000 is pretty low end, but it's pretty typical standard control 120 control panels. But you can also get into 42K, 65K, depending on what's there. And so if you took a normal circuit breakers come in capacity ratings of 10 to 18 to 24 to 35 to 65. They go the whole spectrum, right? And so if you take that and I put it with a starter, just a normal NEMA full voltage non-reversing starter, that starter may only have 5,000 kVA or 5,000 AIC rating, right? So if you took those two together, you have to take the lowest one. So now I'm at 5,000, right? And if my panel needs to be 10, I can't get there that way. So I have to redesign the panel and use components. And so what the manufacturers have done is they've taken breakers and starters and married those together, and then got formalized testing through the agencies to meet certain AIC interrupting. So you're going to hear those terms. I don't expect you to understand or remember all the items that we just talked about here, but just in the back of your mind, if you hear SCCR, that means how is that panel kind of set up, or an assembly within the panel set up, and interrupting capacity is more just related to components. So I know that was probably a lot, but just wanted to throw that out there. Questions on interrupted capacity SCCR ratings? All right, moving on. Surge protection devices. I'm going to throw all my items up here as well right away. So, years ago, everybody called them transient voltage surge suppressors, or TVSS. The latest buzzword now is surge protection device. They're one and the same, right? So it was kind of a little bit of a trick. Is there a difference between the two? According to NEC and UL now, they are both the same thing. So surge protection device is going to be the main topic or main name that you're going to be hearing going forward. TVSS may still be thrown out there, but I just wanted to make sure everybody just knows that they're one and the same thing. They're all designed to take an electrical spike or an anomaly on the voltage coming in and shunting it to ground. Its primarily purpose is to design it or protect any equipment downstream. And most of the time when that happens, it's happening due to probably a storm, right? So if an electrical storm comes through, that's when the voltage will become abnormal and could cause an issue within your system. If the surge suppressors are put in, the surge protection devices are put in, they will normally protect equipment. But I will put the caveat in, if you take a direct hit from lightning, I don't care what you have in the panel, the surge suppressor is going to go, and probably everything else in there, depending on how that spike got into the panel, especially if you have radio equipment or anything that's external to the panel. That's usually a good path for surges to get in. no matter how well we design a panel or somebody designs a panel, direct hits are definitely hard to avoid. But so with a surge device, they come in different flavors, just like circuit breakers and everything else. You can have single phase, you can have three phase, they can be AC, they can be DC. So normally where you see these installed, right? So a surge suppressor, you're going to see, or surge protection device, you're going to see installed on the main incoming line into a panel or prior to the panel. And they'll be three phase or single phase. In a lot of the other times where you're going to see surge installed or put in a panel is any circuits that are leaving a building or leaving that control panel. So if you're in a wastewater plant and you have within your building, you have a bunch of instrumentation, but then you also have a couple devices. Say you have a partial flume, that's outside the building, and you got to run a signal out to that to be able to bring the level of that flume back to be able to calculate flow. You will see more than likely a surge on both sides of that, leaving the building and either out at device, and then so that it can protect the signal coming back. So if something were to get on that, it can short that. It won't take out the input card, it won't take out the input, or it won't take out the device out in the field. But more than likely, if you do hit that, you got to replace that surge protection device out there. I'll just throw out there's basically 4 types of surge protection devices, and they all have their form, fit, and function. Type 1 is primarily to protect incoming power on 3-phase or 120. It's usually upstream of the breaker. So if you have a main breaker in your building or in your panel, those are designed to be upstream of that. Type 2 is designed to be downstream of a main breaker. It does the same function as a type 1, but it's to be downstream of your main breaker, so it's on the load side. Type 3s are really what you'd see in your home if you had a surge protection device that you were plugging your computer or your TV or your stereo system in. Type 3s are basically plug-in type surge protectors. Type 4 is a component, a system component type surge protector. And type 5 are the individual components, i.e. protecting a 4 to 20 or protecting a discrete signal coming from outside a building or that way. So that's just, these are kind of some pictures of some surge. This first one here that I'm kind of highlighting is just a 3-phase. It's a square D standard surge suppressor. The one here is a 4 to 20 on the side. That's kind of a little blurry, but it's a 4 to 20 surge protector going on a 4 to 20 signal. So any questions on surge protection devices? All right, moving on. Phase monitors. So typically phase monitor is designed for single phase, 3-phase. It can detect, under voltage, over voltage, phase loss. They're typically input to a PLC or a controller for control, but they're also hardwired into the handoff auto switch. So typically what you're going to see is you're going to see a surge or a power monitor installed where you're concerned about protecting motor equipment and running off balance, right? So if we lose a phase, if we're an over voltage or under voltage situation, you want to protect that equipment. Primarily, you'll see a lot of these installed in panels that have full voltage non-reversing starters or across the line starters. Typically you would not necessarily need this in a panel if you're running drives. VFDs are designed inherently to protect themselves against these situations, but it's not uncommon to also see them in applications where drives are installed. Another item that kind of goes hand in hand with this phase monitor, I don't have a slide on it, but is also called a power monitor. Power monitors are a little more sophisticated. They have the ability to detect and read and actually output to PLCs the actual voltage, current draw, and everything associated with that particular panel. But they can also be used to detect undervoltage, overvoltage, phase and loss, phase loss and phase reversal. So just a little higher scale, a little more components attached to a power monitor rather than a phase monitor. You know, your typical phase monitor is going to be in that $500 range or less. Sometimes people will say, you know, using a phase monitor, you got a you know, $500 piece of equipment protecting a lot of more expensive equipment. Sometimes these are not as reliable as they need to be, but they will work in the correct situations to also protect the equipment. Questions on phase monitors? Okay, moving on. So motor control, we kind of briefly discussed or talked a little bit on some of this. So different types of motor control. You have obviously your standard starter. You have what they call a NEMA starter, which is pretty well prevalent in the municipal industry. This is the what a NEMA starter looks like right here on the left-hand side that I'm kind of running my mouse over. Right next to that is also a starter. It's actually a contactor, but it is an IEC type. So IEC is more prevalent in Europe. It's smaller scale. What we're starting to see here more in the States is we're seeing a combination of these two, IEC rated and NEMA rated starters. So smaller footprint, not as clunky as the NEMA type starters, but that is what we're calling a full voltage non-reversing, or another term is a cross-line ATL type starter. The next item over here is what we would call an RVSS, or a solid state starter or soft starter. Many of you may have these installed in your panel. They're really designed to prevent inrush on startup. They function, once they have started up, they can function as just a normal cross-line starter. A lot of times these devices will have what they call a bypass contactor on them. So they'll use the solid state portion to start the motor to protect and reduce the inrush. Once it's up to speed, it will switch to what they call just across the line with a bypass contactor. And the reason for that is if you were to keep the solid state starters engaged all the time, that's a huge heat generator. And so now you would run into a lot of issues with trying to offload heat, just like you do with a drive. So sometimes these can be more conducive in panels where you don't want to put the ventilation that may be required for a variable frequency drive, especially if they're outdoors. This item over here is a VFD. So VFDs are very practical. The cost for those have come down substantially over the years. So they're more cost effective in going into panels in which you can control your motor or your pump and drive it at lower speeds, right? And be able to better fit an optimal flow condition rather than just relying on a cross line with on off. So the VFDs definitely have their place in our industry. The biggest issue we have to worry about with drives is the amount of heat that they do generate. They generate a tremendous amount of heat. And so when they do generate heat, we have to dissipate it. So you'll either see forced air ventilation on panels, or you'll see air conditioners being provided. So there's a little bit of extra cost that's above and beyond what a typical panel would require for across the line or full voltage non-reversing with a drive, but there's also a lot of added benefits to providing a VFD as the controller. So any questions on motor control?
Is there an industry standard as far as the number of seconds or the count that it should take to start a motor?
There really isn't an industry standard from that standpoint. What I would say on a lot of that is it's really going to depend on the hydraulic situation that you're trying to control. All right, any other questions? All right, so the next item is transformers. What are the function? What's a transformer really look like? So basically a transformer is an isolator. It's there to provide isolation. It can also provide a different voltage. So where are these most common? Basically in any plant, you're going to have transformers of various sizes. They can range from, 50 VA type transformer all the way up to, 35, 45, 75 kVA if it's feeding multiple panels or sources of current. So typically these are, these smaller ones that are located, that are shown here on my screen, are located within lift station type control panels. It's there to take either 240 or 480 volt power or voltage and drop it down to 120 so that we can provide our control power within the panel. Typical lift station panel, if you have a receptacle that you're plugging in for either powering up a computer or a tool of some sort, these will typically be in the 2 to 5 kVA range. We also have the ability to do what they call multi-tap. So you could have the same type of transformer throughout your system, and it could take a 480 or a 240 or a 208 type input and provide 120 or a different type of power output out of that. In the past, that these can be fed backwards. It's not ideal, but they can be used to go the other direction. So they have names for some of these, a buck boost, or that those are some of the names that you may hear associated with transformers. Questions on transformers? All right, moving on. Power supplies. What are power supplies? What do they look like? What are they used for? Oops, sorry about that. So power supplies, also used for isolation. They are provided in panels to go from a 120 VAC or AC power to DC, so direct current. So it's not alternating anymore. And your typical voltages that you're going to see in a panel are 24 volts and or 12 volts. These are used to power instruments. So if you have a pressure transmitter out in the field, more than likely you will be sourcing 24 volts power from a control panel to that instrument. They're also there to provide power for barriers, Ethernet switches, your PLC controllers, radios, a number of items that can be located within a control panel. The power supplies can also be married with what they call backup power. So you can put a battery in there and tie the two together to provide 24 volts or 12 volts DC, depending on how you set the panel up for backup power. Now, you've probably also heard, and I don't have a slide on this, are what they call UPSs or uninterruptible power supplies. Those are normally 120 rated. They're big. They've got batteries inside those as well. They do generate a lot of heat. The one issue I would say with using a UPS, they're great in panels within buildings. where the buildings have, climate controlled temperature. If you get outside of a building that's climate controlled, the power supply with the DC to DC converter that these power supplies have, and putting a little gel cell type battery out in the field where there's a lot of heat that can be generated, the temperatures can fluctuate a lot. Those type of battery backup circuits work much better than a UPS out in the field, right? If it's outside, if it's in a lift station, it's exposed to extreme temperature changes, UPSs will fail quickly. They're not designed to take the wide variance of temperature. And so that's why you'll see in a lot of panels, a 24 or 12 volt power supply married with what they call a DC to DC converter, or it may be just a battery backup UPS that's in there. That's what they call them, with a little battery mounted in the panel. That's a very common practice. And so if you see that in your panel, that's essentially what you have. Questions on power supplies? All right, PLCs and controllers. Kind of what's the difference, or how do we distinguish between them, right? So a PLC is a programmable logic controller, custom programmed for so if I have a lift station, I need to control 2 pumps. I put a Allen Bradley, Schneider, GE, you name it, type controller PLC in there. Those are usually associated with a custom program that has to be downloaded in by somebody that can program. Whereas what we're calling controllers, they're normally a fixed purpose, or they can be configured. So they are application specific, and you basically pick and choose how you want those to operate. So couple things here. So this one on the left is an Allen Bradley Micrologix controller, PLC. The ones in here kind of in the middle are some what we would call controllers. So it's got a specific purpose. The one in the middle is basically a duplex pump controller off of floats. The one on the right can be up to a triplex using a transducer for control. It can also have float backup, but basically with this controller, you pick and choose how you want it to operate. If you want a duplex, triplex, simplex, all the variables, there's no custom programming that has to be done. So you'll see all different types of flavors and makes in various panels, but just kind of the way the industry kind of treats these is there are PLCs and then there are controllers, and we kind of differentiate the two between a PLC is custom, a controller has got a fixed purpose. Questions, PLCs, controllers? Moving on to intrinsic safety barrier. We touched a little bit on this, but what's the purpose of intrinsic safety barriers? Intrinsic safety barriers are designed to protect equipment that is installed in what they call a hazardous location. So in our industry, municipal water, wastewater, hazardous locations are going to be lift station wet wells. They're going to be headworks buildings in plants and those type of scenarios, and other areas that can be classified within a plant as hazardous. So you'll hear the term Class 1, Division 1. You'll hear Class 1, Division 2 type location.
Modified or unmodified?
Unmodified.
Really?
Yep.
How's that work?
Somebody's got their mic open.
Actually, the glass bolts are made to be cut and extracted for new ones.
Hey Jim, can you mute yourself, Jim?
Really?
Didn't realize all that.
You're gonna replace all of them?
Well, just ones on the bottom.
Okay.
I am going to take and mute Jim.
So we're all good there.
Good news.
Sorry about that. The power that you have as a presenter, you can just go and mute them. So So okay, on IS barriers. So typically you're going to see those going into, like I said, hazardous locations. There's a forms of an IS barrier. You got what we call discrete or on floats, or another term that you'll hear is a simple device. A simple device is defined as a float switch or a contact in a hazardous location where stored energy is not available. And then you also have what they call a non-simple device, which is like a pressure transmitter or submersible level transmitter that can be in a device in a hazardous location that could store energy. So what you're trying to do is you're basically limiting the current that can go out to that device that could cause a spark or ignition of hazardous flammables. So whether it's gas, whether it's methane, any of those type of things that are located in there, you're trying to prevent that from happening. So in a control panel, these are what the barriers are going to kind of look like. In these two pictures, you can see that the barriers are installed in a different location in the panel, and they actually have a shield around them. That was standard practice up until a couple of years ago, in which NEC and UL relaxed that. Barriers are no longer required, but there now is a 2-inch air gap around any of the intrinsic safety areas that are required for installation. And so most of the time what you're going to see is you're going to see light blue wiring coming in where it's still on the hazard side of the barrier. And then on the downstream side of the barrier, it will go back and revert back to normal panel wiring. So you can see here some red wires side. So this is considered the safe side of the barrier. This is considered the non-safe, and it's always identified industry standard UL's requirements, light blue wiring. So those are kind of the safety barriers. You're going to see two types, discrete and analog. The issue with the analog is they have to be married with the device. The device that you're tying it to has to have entity parameters to prevent that stored energy. So just kind of giving everybody an idea of IS barriers. Any questions on IS barriers at all? All right, moving on. So this is just a slide. I know it says single compartment. We've got a couple 2-door enclosures, but just different types of control panels that you can see out there. There's different flavors, there's different looks, there's, you know, panels that are on legs. And normally the legs are mounted in, you know, there to give the air gap required by each different state. Normally it's 18 inches, some have 24 inches. But to get the required air gap, if it's installed right over, say, a wet well or something like that, so you have the ability to off gas anything coming up prior to entering the control panel. And sometimes you will see skirting across those. Here's typical wall mount type panels. These panels will range from what they call a NEMA 1 or a NEMA 12 panel, which is kind of like this one right here. It's a steel, just a cold rolled steel painted gray. This one, you can't see it, but there's also what they call a NEMA 4X panel, which is stainless steel more times than not in our industry. It can also be fiberglass, but it's designed to be installed in corrosive or outdoor type applications. And the stainless steel versions can come in 304 or 316 type stainless steel. 304 is more cost friendly than 316, but 316 is also a more pure stainless steel and will resist rusting and pitting more than 304. So 304 has got a little more irregularity in the steel and could cause some rusting issues. especially if they're in high salt areas. So that's kind of single compartment, and then you can get into what they call multi-compartment. Motor control center lineup over here is considered multi-compartment, multi-buckets. There are panels that have specific compartments and components that are isolated. This one here, you've got your main power coming in. You can have your what we would call motor control in one compartment that's completely isolated from the other. And then you could have your control circuitry on the other side, even isolated further, right? So the nice thing about multi-compartment control panels is if you isolate your 480 or your 240 or what we would consider your higher voltage power coming in from your 120, somebody may be able to, may feel more comfortable going into a 120 panel or a 120 compartment to work on something rather than having to get another person or electrician to come out and work on 240. So by having multi-compartment, that person may be able to go in and work on the control side and not have to worry about going in on the higher power or higher voltage side, the 480 or 240 system. So just kind of look and feel of different panels. Just want to throw that out there. And the next slide is going to be kind of any questions. We're kind of towards the end of the presentation that I had put together. So if there are questions on things that I didn't cover or things that I did cover, I'll open it up now.
Does anyone have any questions for Todd?
Easy crowd today.
Yeah, no kidding. Definitely Friday.
It's definitely Friday. And if the weather is anything like what we have going on here in Minnesota, in Illinois, there might be a lot of people playing hooky this afternoon.
Yes, it's beautiful here.
Because we know that is coming to an end.
Well, I'm going to do a wrap up here, Todd, with the presentation, but I think at the end of this, if you don't mind, you didn't really mention anything about what SJE, the services that you can provide. So I'm going to allow you to give a brief plug after I talk about how to obtain a certificate here.
Sure, absolutely.
So the link for this recording will be posted on our HOI YouTube channel soon. Give us a little bit of time for Todd to get the recording sent over, and then we will get that posted. So probably next week, maybe sometime. After you view this presentation, if you would like credit for operator CEUs, you can email me, Brandy Young, or you can also email Jason Naylor with our organization. His email is jnaylor@gpsd.org. That's jnaylor@gpsd.org in order to obtain your certificate. And again, remember that only paying members can obtain certificates for CEU credit. So if you have not paid your 2020 dues, but you would like to obtain some certificates, you can still pay for this year. Also, remember we have an HOI channel on YouTube, and past presentations are still available for viewing, and you still can obtain credit for those as well. So head on over to YouTube, the Heart of Illinois YouTube channel. Okay, turning it back over to you, Todd, for a wrap up on SJE.
Perfect, thank you. So SJE is our parent company. As you saw going through some of the slides here, there was a mention of Primex, which is one of our brands within SJE. We're located, our headquarters is in Detroit Lakes, Minnesota. We have 6 locations throughout the US. So we cover everything from septage alarm panels all the way to large system integration, multi-million-dollar projects for system integration. We are represented in Illinois and Northern Illinois by Gasvoda and Associates. In Southern Illinois, we are represented by Hydrokinetics and Van Eventer Engineering. So we cover the complete gamut. We are probably the world's largest float switch manufacturer, which people don't necessarily associate with a lot, but if chances are, if you go into Lowe's or Home Depot, the float switches that are on a sump pump there are manufactured by one of our brands, either SJE Rhombus or CSI. Those are our other two brands that we have. But for the most part, on our engineered solutions for control panels and system integration, the branding is Primex, and we cover the gamut from lift stations to water plants to small little starter panels to, like I said, multi-million-dollar system. So that's kind of a little plug on SJE.
Okay, thank you so much. Thank you, Todd, for your presentation. And I will see the rest of you HOI members later. Thank you.
Thank you. Thanks, everyone.
Thank you.